Hello everyone, I'm Dr. Hussain Haydari, and today we're going to continue our discussion on polymers. We already talked about some basic chemical structural features of polymers. We talked about the units, the monomers, that are used to build up these long chain molecules called polymers. We also talked about some of the properties of these polymers. We discussed how crystallinity could come into play and influence the properties of a polymer. We talked about molecular weight, some of the calculations associated with that, which you saw some examples of that, or if you haven't, you will in the first quiz for the polymer section. Today and during the course of this week, we're going to talk about more of the properties and characterization aspect of polymers. We're going to talk about the stress-strain behavior of polymers, different types of behavior. We're going to talk about ways to process polymers, manufacture parts out of polymers. We're going to talk about polymerization reactions, which we briefly touched upon in more detail. And so it's going to be a week more on the processing and understanding the behavior of polymers rather than just understanding their structure and composition, which we did during the first week. So the questions that we're going to answer are, first of all, in terms of characteristics, what are the tensile properties of how do they perform mechanically, and how are these connected to their microstructural features? So how does structure connect to the performance and mechanical behavior of these materials? We're going to talk about some of these polymers and how we can actually induce some properties into them. How can we harden them? How can we anneal them in order to achieve better properties? We're going to talk about how temperature and other environmental factors influence these properties. And we're also going to talk about ways to process and make parts out of these polymers. So it's going to be on more of the behavior and processing side. So to start, I'm going to first pick up on where we ended last time, which is some of the most common polymers that you will see. This is a good practice for us all to look at the structure and try and see if we remember stuff. So polyethylene here is basically a repeat unit of C2H4. Okay, so it's the ethane unit that you've got repeated. If you change one of those hydrogens for chlorine, as we showed previously, it completely changes the performance of this polymer. So it goes from polyethylene to PVC, which is used in tubes and construction. And so if you change those hydrogens out, if you swap them out for a fluoride molecule, a fluoride atom, you would actually see that it also completely changes it. PTFE in this case is a material that's extremely temperature resistant. It doesn't melt all the way up to 300, 370 degrees centigrade. So it's a pretty good thermal resistant material. And then you've got polypropylene, and you saw how polypropylene and polyethylene differ in terms of their chemical resistance. And the only difference is really that CH3 group that's replacing a hydrogen on polyethylene. So we kind of saw how a tiny structural change can completely change the behavior of these materials. We didn't systematically look at that. It's a rather detailed chat to have to go into each of these modifications and understand how the electronic structure of these atoms and the bonds influence the some of these special properties. here in this chapter, we're going to try and delve a bit deeper into why these sort of phenomena happen. These are a couple more examples. We came across polystyrene before. You saw that that ring there can also influence the ability of this bond to rotate. So we also talked about isomers, and this was one of the cases where we made a distinction between conformation and configuration. And so we realized that some of these changes of the orientation and relative positioning of these chains cannot be achieved because it's either a double bond that's enforcing it, or there are side groups like the ring that you see here in polystyrene that actually doesn't allow you to do a lot of range of motion here. So another example is PMMA. So PMMA, very common material to dentists. It's used a lot. And here you can see the structure of it. It's an acrylate-based, methacrylate-based polymer, so it requires light to cure. And then we will discuss this certain material in a bit as well and its special properties. Phenylformaldehyde, this is another material which is quite interesting. Formaldehyde itself has a rather semi-crystalline structure. When you add phenol to it, it changes it. And so you can actually see that this is sort of an example of a copolymer. So in other words, you've got units connecting formaldehyde together. And so we also discussed copolymers in the first week of our lectures. We may see more of it coming. And another example that you see here is nylon, and we kind of looked at some of the special applications of nylon. It's really strong material. Nowadays, you're able to even 3D print it, but it's an extremely useful material in strength. We'll be looking at that as well. PET, polyester, got a rather intricate structure. So you can see that some of these, unlike the ones on the first page that I showed, that had only a C2H4 unit, that we had swapped out the H hydrogens with some other atoms. Here you have a lot more complexity. And you can see you've got lots of these rings added, and then you've got some carboxylate groups and so on and so forth. During this course, it's an introductory one. We won't be looking at how each of these units across this monomer part of the chain influence the entire folding and basically bonding and everything. But we will try and briefly at least touch up on some of these. And polycarbonate, another example too. We will talk about these materials, especially the distinction between amorphous and crystalline is something we're going to emphasize a lot this week. So let's talk about properties. So we're especially interested in mechanical properties. You've had a bit of this going on in the metals part. Here we're going to look specific polymers, but before we do that, I'm going to just have a recap. What we've seen in metals is that you have a sort of a linear region at the beginning, sort of a linear elastic region. And so you extend it. If you let go, it can actually go back to its original position. It's sort of reversible until you reach this necking point, and it yields basically. This part here, this point represents your yield strength, and then you can continue beyond that. You have a necking sort of phenomenon happening, and the cross section is reduced, and then you can still continue stretching it beyond that point to basically high strain, net strains, and then you can actually observe it reaching the point of fracture beyond that ultimate strength. So you have basically elongation at break here, and before it reaches that elongation, it's got an ultimate strength happening at some point here in between. And so this is the typical behavior of the stress strain curve of a metal. Now, how do polymers differ? So polymers, of course, you kind of have an idea right now of their structure. You can imagine that they, a lot of them at least, could be a lot more plasticky and a lot more elongation we expect. We expect them to be probably, you know, a bit less stiff than metals. So let's see how these actually are. So in fact, polymers have distinct behaviors as well. So you can have brittle polymers that behave a lot like other brittles. You have plastic polymers that have more of that elongating plastic behavior. And then you've got elastomers that have an extremely different behavior. They just elongate a lot more, but apart from that, you can see that the the curvature of this plot, it's upwards, and you can see that it's all increasing in terms of its stress bearing as it elongates. So it's pretty interesting how these differ. So the first thing you can see in general is that their failure strength, or basically the stress at which is typically a lot lower than metals. So if you remember with metals, you have at least hundreds of megapascals in terms of the maximum basic stress they can take, or in terms of the mechanical strength. Here you have, you know, around tens of megapascals, as you can see. Now, another observation is that the elastic modulus is a lot less than metals. Yeah, metals are a lot stiffer. You don't get this much deformation with this small of a stress. In metals, you have to have a lot more stress to reach elongations way smaller than what you see here. And another thing here is that, again, as I mentioned before, this elongation is a lot more. So you can have elongations as high as a couple 100% or maybe even 1,000% elongation, whereas in metals it's, you know, maximum a few 10%. So now this, again, which of these polymers that we've discussed belong to which group is what we're going to talk about today. So let's first look at how these three different types of polymers behave in a point-to-point basis, like what you've already did with metals. So let's first look at brittle failure. So this happens in the shape that you see here. Basically, if you do that tensile testing, you'll see that the specimen has a very sort of a gritty crack there, and so you can actually see a sharp boundary there, and it happens rather fast in terms of elongation. It doesn't increase in length that much. What's happening here is actually you have a material that's either very crystalline, it's got a perfect network sort of polymer, or you've got a highly cross-linked. You remember we kind of compared these different materials, and we saw that if you start from just linear chains, moving towards these secondary cross-links, and then towards a more network structure, the strength is always going to increase. And so both the highly cross-linked and the network polymers have sort of brittle failure performance. And what's happening there is that you actually stretch them until they're all, you know, elongated as much as they can be. These network pores or microstructural lattices are actually going to elongate as much as they can. These crosslinks are gonna, these crosslink meshes are gonna expand as much as they can, and at some point it's going to give up and break. So it doesn't elongate as much as you would like a polymer to do, but it has more of a brittle behavior, and it can actually withstand a lot more stress, so its tensile strength is typically much higher than the plastic failures. Now, what happens in the plastic case is a bit interesting, because this is something that you also see in metals. It's not that different. In plastic polymers, what you have is actually similar to the necking behavior. The region where you can see in this image, it has become kind of whitish. You stretched it quite a lot, and so it's like when you stretch chewing gum, you can see the color. What's happening here is that you've got a semi-crystalline polymer. So unlike the aligned, highly cross-linked and network cases, here you've got sort of a semi-crystalline structure. And you've got, again, to remember what that means. A semi-crystalline structure is a structure that has amorphous regions and crystalline regions. Well, so these amorphous regions that are sandwiched or mixed in between the crystalline regions are going to get stretched. So as you continue exerting higher stress levels, you can actually see that it goes, it stretches out those amorphous regions, and they're just going to elongate and get more and more aligned. So what's going to happen is they're going to get aligned further and further, and it's going to be able to now withstand a lot more stress until it reaches a region where now it's fully utilized or saturated, that elongation coming out of the alignment behavior, and now it's just going to have that sort of plasticky sliding behavior where these crystal regions are going to slide across each other, and those aligned regions are just going to act as these sliders. So you're going to have some sort of a rather interesting slipping behavior there. So that's why it can actually withstand these high elongations, but not anymore in terms of stress. So you can see that the stress level kind of plateaus, and like it doesn't go beyond that point. That's really the strength of this material right there. Beyond that point, it's just sliding and slipping and actually elongating. So that's why you have some rather special behavior in these semi-crystalline polymers. So we're going to talk about the last one, which is elastomers, in a bit. But before that, I'm going to take a look at some of these examples that we mentioned before in terms of their properties. So this table kind of has a lot of these polymers included. So we're going to look at how they differ. So firstly, you can see here the elongation at break. Okay, it varies quite a lot. So already before I've even told you which of these are semi-crystalline, which are actually network, you can kind of see that brittle versus ductile plastic behavior already in the elongation. So some of these have very high elongations, even up to 1,000, 1,200. Some of them have a very small amount of elongation, just 1%, 2%. And so you can already see that here. Another indication that you can use if they give you the properties and they don't tell you whether these are thermoplastics, whether they are plastics, whether they are brittle, you can tell is their tensile modulus. Okay, so you can also see quite a range here. So if you remember, in terms of the ones that had brittle one, the slope was a lot higher. So you can actually see that increased slope means increased elastic modulus. And so in this case, if you have elastic modulus a bit higher, elastic moduli as large as 2.7 here, gigapascal, that is a rather stiff material. So I would expect that it has a brittle behavior, and it does. Okay. Versus where you have 0.1, 0.2, and you would expect the stiffness, the slope to correspond to those materials that have more of a plastic behavior. And you can see it here. I'm going to go back here real quick. What I'm talking about is the slope at the beginning. And you can see that it's pretty steep, especially if you compare it with elastomers, which we had. So, okay, so the next property here is the strength, okay? So we've got the tensile strength and the yield strength, okay? So typically more of a trend in plastics, as you can imagine, because those actually yield. The brittle polymers don't, so they only have an ultimate strength. So again, if you look at these, you can kind of see that, right? So you can see that here, for instance, like, let's take one of these that has quite a lot of deformation. You can see that it doesn't really go beyond the yield strength. It actually drops even a little bit when it moves through that elongation region. So that's a plateau that I was talking about earlier, is that it reaches its yield strength, it starts that necking behavior, and then it never reaches a high stress amount. It just goes to a plateau and even drops in a lot of these cases. So, okay, so now we're going to talk about what these are. So, okay, so I already mentioned this semi-crystalline polymers. Here are the examples out of this table that are semi-crystalline. So these actually have sort of a plastic behavior, okay? And these are, I can say they're the dominant type of, they have the majority of these polymers of this type. So polyethylene, both low density and high density, PTFE, polypropylene, polyester, nylon, these are all thermoplastics that are semi-crystalline. So they have this plastic behavior. Furthermore, if you increase the temperatures we already mentioned, they tend to deform quite easily. So you can see that all of these have very high elongation at break values, hundreds of percent increase in length. And then you can also see that if you look at the appearance of these versus the crystalline ones, they're a bit more opaque, okay? So they have rather a, better said, translucent sort of look rather than a fully transparent one. Another dominant group is thermosets and amorphous thermoplastics. Now, if these amorphous thermoplastics are highly cross-linked, they form a rather brittle mesh. So again, thermoplastics can be amorphous, or they can be semi-crystalline. They could be closer and closer to crystalline, but as I've mentioned, we don't have 100% crystalline polymer. So the amorphous ones, we will see how they differ, but basically if they cross-link to a high degree, similar to a lot of the thermosets, they can have a rather brittle behavior. And this is what you see here. So now, if you look at their elongation, they're going to be really small. So only maybe the maximum here is 40%, 80%. That's actually quite exceptional. They usually just a few percent. You've got also a really high percentage, I would say, with these brittle materials at 110%. That's quite a lot. But again, you can see it's distinct. The distinction between these two, these are hundreds of percent, so they can go up to 1,000. These max out around 100, and even that is quite a lot. So there is another polymer in this group here that's rather special. So I already brought that up earlier, but phenol formaldehyde, it comes from the mixture of phenol application. Phenol formaldehyde is a thermoset material, and it's got a network structure. So network structures are rather rare in polymers. And as you can see here, coming from that particular structure, you get a rather brittle behavior, okay? And you can see that it doesn't really yield at all, so you can't really measure that. and you've got a tensile strength that's rather high, I would say, by the standards of polymers. So you can see that in general, all of these polymers, the ones that you probably hear about in the future, polypropylene, polycarbonate, polyester, nylon, phenylformaldehyde, you might hear about it, polyethylene, really common. These are the ones that you will probably come across many times in your career. And these are the ones that you really have to have good understanding of how they perform mechanically and why that is. And now you can see that that originates from their structure. Okay, so now we're going to move on to elastomers. Okay, and elastomers, as you know, they elongate quite a lot. So you can see here, this tensile test here is pretty fun working with these materials. They can go forever. Like literally, you can see that this is elongating easily to twice, 3 times, even 4 times its length. And so they go through this rather, I wouldn't say exponential, but sort of up-facing curvature regime. And what that means is that as you stretch them, they become more stiff. So the slope of this curve is going to increase as you move forward. So the way this happens is that you've got a lot of these amorphous chains again, but they aren't that highly cross-linked. So they start getting, you know, a little bit more aligned, but basically you get them stretched until they reach a really, you know, elongated state, and you can't really stretch it beyond that, and it fails if you do. So this is basically where it terminates, breaks. So that is far off from where you started. It can have, you know, 800%. So elastomers, like rubber, basically, are really common. So we will talk about both elastomers and plastic and brittle polymers in terms of how you can manufacture parts with them and how these properties influence their processing. But for now, I think this, in terms of a good introduction to stress strain behavior, is a good place to start. I think I'll talk about this also, and then we'll finish this first lecture here, and we'll continue on in the next lecture. So this will be our last slide here. You can actually, what this slide is telling you is that you can actually utilize this change of behavior or mechanical performance in order to enhance the properties of a material. So, for example, you saw how when you stretch these, the slope can actually change in a lot of these materials. You can see how these long chains can get aligned, okay, into a more of an aligned and crystalline sort of structure out of that rather random amorphous state. So if you actually utilize that in order to plastically induce a better mechanical property, that would be called drawing here. So when you draw a piece of plastic, it means you stretch it until it becomes, you know, the fish lines, the monofilament fish lines. It's such a thin strand that it's actually been stretched to a point where all of those chains have aligned into this really thin fish line. And so that gives it the strength, the elastic modulus that it has. So it both, this process increases both the elastic modulus and the tensile strength, but of course it decreases ductility. So ductility here, what happens is that you've already stretched it quite a lot, and so you can't really go any further. So once you've already utilized this elongation here and you've taken it to its maximum elongation, you can imagine that there's not much more remaining. So it becomes rather brittle at that point because you've already utilized its ductile behavior. So that is why these two increase, but in terms of its ductile behavior, it decreases its ductility. So another process here is annealing. And you typically do this after drawing. Now, annealing belongs to the family of thermal processes on polymers, and we will look at that in detail in the next lecture. But for now, I'm going to tell you that they use annealing, which is a thermal process, after drawing to kind of relax it a bit. And what it does is it heats it up, it reduces this alignment there, it decreases it, but although it reverses some of that, it kind of finalizes that material. And sometimes you need some relaxation, but sometimes you don't do this process. So what it does is basically the opposite of what you do in drawing. It takes away that alignment and it actually reverses drawing. So this part we're going to look at a lot more detail, but this part is basically utilizing mechanical stresses that induce structural changes to actually improve the performance of a material. And this is really common in polymers as well as other materials. So I'm going to leave it there and we're going to continue in the next lecture. So take care.